Hi everyone, I'm Walter, a PhD student from SDS department at UT Austin, and today I'm going to talk about benchmarking cosmological surrogates beyond Voxelwise error. So to start with, I'm going to briefly talk about what are surrogate models and why we need them for cosmology. So to think about like the world without surrogate models, if we want to predict the final density field from the initial conditions with some cosmological parameters, we usually throw them into a simulator and it solves a series of complicated partial differential equations to give you the final results. This is really accurate but really slow, as one full simulation run could take hundreds of CPU hours. And we won't be able to afford all this run if we need more data and under different settings. Therefore, we want to develop the surrogate models or the machine learning based models that act as fast approximations of our simulator. In that case, we could get the data in an easy way, like in only a few hours, and we could adapt all these settings and rerun this training and generation scheme so that these data could be adapted for different downstream tasks. However, not all surrogates are useful, so they are only useful if they are both, say, fast and also preserve the scientifically meaningful structure, which leads to our next question. What should count as a good ML surrogate? Many machine learning-based models often use Voxelwise losses for training, like a mean square error, MSE, which measures the local element-wise difference between the predicted density field and the actual density field. However, scientists in this field care more about the global structure across the different physical scales, like power spectra. There is a natural mismatch between these two quantities. Therefore, we want to provide a benchmark to test whether the machine learning surrogate models are actually good in both of these metrics. And we have our Quijote benchmark set up here, which is built based on the Quijote Latin hypercube simulations. They are 3D dark matter density field data, and we use the resolution as the 64 cubed. The inputs are initial conditions, density fields with the cosmological parameters, and our target is the final density fields. So we want to let our model learn the generation process and to predict the final density fields given the inputs, and we can compare the actual performance between the actual density fields with the predicted density fields. In our model family, we have 3D UNet and ResNet as the very popular choice in computer vision. We also use Fourier neural operators as a representative from the neural operator family, and we also add some regularizer based on power spectrum, because power spectrum is something we really want to measure and want to see if regularization on this explicitly would help. For evaluation metrics, we have both Voxelwise and physical metrics. The Voxelwise are MSE and VRMSE. For physical metrics, we have power spectrum ratio, and cross correlation between power spectrums. And these are the results for the scalar metrics like MSE, VRMSE, and the power spectrum loss, and the R2 R square score, and the mean RK. So from this table, we could see that UNet3D and ResNet3D are still the best behaving models, speaking of both voxel-wise error and the physical errors. And adding regularization terms on the power spectra explicitly actually doesn't help. So the UNet3D and Fourier neural operators, when adding regularizers, they actually behave worse in both the MSE and the power spectrum loss. And FNO as itself is not as good as the computer vision based, like CNN based models. And these are some visualizations results. So the one on the left is the power spectrum overlay, where we want to predict the actual power spectrum. So the dotted lines to choose and all the different curves are the predicted power spectrum from different the power spectrum from predicted density fields from different models. And the one on the right is the loss curve of the power spectrum loss, and the bands there are the empirical distributions we have from the 200 test simulations. So our conclusion is that we really need a domain-aware evaluation for the machine learning surrogate models, especially for cosmology. And through our experiments, we proved that architecture matters, domain metrics matter, and regularization may not be a shortcut. These results are still preliminary, and in our next steps, we hope to add more baselines from the classical numerical methods and the generative AI methods. And we also wish to scale the benchmark to include more data and broader settings like combination studies. So thank you. And if you have any questions, feel free to contact me through this email. And